Hello, I'm Jeff Barney, and I'm here at the Remcom booth at IMS 2016, and we're talking to engineers about matching network design. One of the challenges that we've found is that engineers are trying to figure out what component values to actually plug into the matching network layout. So if we look at this example, it's a GPS Bluetooth antenna. There's a matching network that is already laid out, and there are 2 inductors and 2 capacitors. And so the challenge is, what are the values of those inductors and capacitors that need to be applied? So you can look at the graph, and often engineers will use a schematic layout tool like ADS or Opteni to figure out what that topology should be. And the schematic will provide a nice prediction. So here we can look at the blue line and see that there's a nice match in the lower band and in the higher band. But then once you physically lay it out and prototype it or take a measurement, you're going to find out that that resonance shifts. So here in the higher band, it moved out of band, and then in the lower band, there's no resonance at all. So what Remcom is offering is a new capability through simulation that we're referring to as full wave matching circuit optimization. And how it works is that we start out by computing a response matrix. And so what we're going to do is we're going to take the layout, the full matching network layout, and the 3D physical model, and we're going to run a series of full wave simulations that characterizes the waves and the fields. And what that's going to do is allow us to figure out what is affecting the circuit components. So what kind of antenna is coupling, what kind of coupling is happening from the antenna down onto the matching network, and then any kind of interactions within the matching network itself. So once we have that system characterization, we can then move on to the next step, which is going to be optimization. So we're going to define our thresholds. So here we're looking at S parameters. In the GPS band, we want better than a 4 dB match. In the Bluetooth band, we want better than a 10 dB match. And then we're also going to provide the allowable component values. So we can say the capacitors are allowed to range from 0 to 10 picofarads. In the inductors, we can select any value from 0 to 10 nanohenries. Once you run that optimization, you're going to wind up with your output, and the output is basically which component values provide the optimal match that you've defined. So here are the 4 values, the 2 capacitors, the 2 inductors, and that's going to provide the match in the 2 bands that we were looking for. So from an engineering perspective, this kind of takes the guesswork out of it, because we're allowed to analyze hundreds or thousands of different combinations, where if you're in a lab, you can only check a dozen, 2 dozen combinations if you're building prototypes and taking measurements. So that's just one quick example, but we also have advanced topics where we can support multiple configurations. So here we have an antenna that's being held in a hand or up next to the head. So we can optimize simultaneously over these 2 cases and figure out what the optimal component value should be. And then we can also consider tunable components. So if you have a tuner that can take on multiple states, well then we can support that as well and tell you which value should go with which state. So if you have any questions about this, feel free to stop by our booth or stop at our website. We are more than happy to talk about this with you, run some benchmarks with you, and just give you more information about what this capability is. So thank you.